All right, let's get back to the Bakry-Emery criterion. So just sort of for this lecture and the next lecture, I don't know what other way to put it, but it's going to be somewhat boring because it is going to be calculations. So I'll just give you a roadmap ahead of the next 3 or 4 lectures. Okay. Today, I'll do the Bakry-Emery and maybe stop the log Sobolev. Next class is a log Sobolev. With that, we'll end this whole arc of theory. And then we're going to switch to a different view. Then I'm going to go back to autoencoders and GANs and the design choices and architectural choices. Then that will lead to sort of from there, I'll go to a diffusion model and then talk about when I talk about VAEs and GANs, I'm going to talk about elbow lower bounds, and we'll see how that sort of gives the architectural choice for a denoising network for diffusion. So we are going to go along a different route for the next block. So then we'll come back to theory for a block. So this class is going to sort of oscillate between sort of different views. This class and next class is about we'll sort of close the first theory sort of arc of this class. Okay. So the today's class especially is going to be very, very nitty-gritty calculations. You could argue, why am I even actually showing this? Can't I just ask you to read it by yourself? 2 reasons. One is that I don't think you will if I ask you to. Okay. So at least it's a good idea to see some things of these calculations of this. 2 is that I think it is worthwhile. So these are important results. You look at it, at least to me, they look magical. So looking at the proofs somewhat demystifies what the magic is and why this is happening. Okay. Even though it's just very detailed calculations, it's worthwhile to see it once to just see why are these kinds of things true. So I still am going to do, I'll not do every single calculation. Some of the way more painful ones, I will just leave it. But at least you'll get a sense of how these kinds of proofs go. Okay. So with that caveat, let's come back to Bakry-Emery criterion. Here I'm again following, the heck, I hope it doesn't crash on me and reboot this computer. The UTs, okay, I shouldn't say anything, it's recorded. All right. Okay, apologies if this whole thing reboots at some point. These computers have a habit of some software update is needed. It may just decide to just disappear on me. Okay. These are essentially a set of homework problems in Ramon van Handel's probability and high dimensional lecture notes. And there's a very kind group of graduate students somewhere who solved many of these and put it on GitHub, which I found, which I've heavily borrowed from and sort of added a little bit to it. But essentially, it's based on that, and these are the links for this. So the goal is, as I said, we want to, today's going to end with the following Langevin dynamic, which is the Markov process. Grad log pi star is the drift. The diffusion is just √2. The invariant measure of this pi star is e to the minus v normalized by some constant. We are going to assume that v is rho strongly convex. And in this case, we want to show that sort of it's fast mixing independent of dimension. That is the arc for today's class. Okay. In particular, we are going to do this by the following. We will show that variance mu of f is less than or equal to 1 by rho times the Dirichlet form. We know that from Poincaré's from the theorem last time, because we have established this Poincaré inequality with parameter c equal to 1 by rho. It means that it converges exponentially fast at rate e to the minus c, which is e to the minus 1 by c. 1 by c is rho, and so that's you got dimension independent mixing. Going back to Konstantin's question last time, why do we need any additional machinery? Can we show this directly? Well, what's variance mu of f? It's an integral, right, with respect to the stationary distribution of some f square minus the mean of f square. This integration, if mu was a Gaussian, we actually did these things explicitly when we did the Gaussian computer variance for the Gaussian and so Dirichlet form for the Gaussian. In general, with some distribution pi star, you can say it's this integral, but to actually manipulate it further is not trivial. Okay. Same with the Dirichlet form. It's also an integral. What we will do today is we started this chain last time already. I'm just repeating this this business, that we will establish the Bakry-Emery criterion, which is a differential inequality. There is no averaging with respect to mu. It says you define certain operations based on the semigroup generator and the push forward operator. Okay, both of which you can say much more explicitly. And once you have with these two operations, we will establish an alternate criterion which implies the Poincare inequality and thus implies fast mixing. So this is really the power of the Bakry-Emery criterion. And we are going to do these calculations by the end of today to see what I mean by they're just algebraic manipulations that are needed. Okay. By the way, is the sound, I forgot to ask, online, is the sound coming through fine? Otherwise, I presume somebody would have complained, but is everything okay? If you could, somebody could let me know, that would be useful.
Yeah,
okay,
good.
Thank you. So that's the goal. And so, as I said last time, the key construct was this Carré-Duchamp, which Gustavo pronounces with a much more throaty, but I don't know how to pronounce it, so I'm just going to call it Carré-Duchamp. Okay, and this is basically the following. It's the gamma of fg is L of fg minus flg minus glf by 2. We have talked about this last time. We also saw that we did this for the OU process. We stated that this is nothing but the grad f whole square, the 2 norm. Okay. Note that there is no integral with respect to mu or any such thing. It is just grad f square. Okay. Constantine? Okay. All right. We started proving some properties. We actually proved these properties last time. The first was that the integral of the Carré, if you just average the Carré-Duchamp over the entire, with respect to the measure, you'll get the Dirichlet form. So it's essentially a differential form, quote unquote difference. It's inside the integral, okay? Whether it's a differential form or whatever, it's this thing, it's inside the integral. And we actually proved that last time. We also showed that the Carré-Duchamp is non-negative. We did this last time, which used a sort of Cauchy-Schwarz-like inequality. And that's where we ended. So let's continue. So far, it's just a summary of what we did last time. So let's now move forward from here. So recall the Poincare inequality. It said the variance is less than C times the Dirichlet form. So what is the variance? Let's zoom in a little bit. Variance is nothing but the average expected value of f square minus expected value of f, the whole square. That's the variance. So we can think of this equivalently as the following. Remember the push forward all the way, because in stationarity, you can push it all the way to infinity. You can think of this as p infinity of f square. I've just rewritten it this way as using the p at time infinity. P infinity of f, the whole square. Similarly, the Dirichlet form is nothing but the integral we saw right now. It's the integral of the Carré-Duchamp over the stationary measure, which can be thought of as the infinite push forward of the Carré-Duchamp. It's just another way to write the same thing. Are you good? I'm just rewriting this. In which case, we can look at, if you think of this as sort of an asymptotic Poincare inequality, then you can quote unquote think of a non-asymptotic version of this, where instead of infinity, you replace this by t. Okay, you may not get c, so everything is t dependent now. You can look at so this is what we mean by a local Poincare inequality. Instead of looking at p infinity, look at pt of f square minus pt of f the whole square less than or equal to c of t, pt of the Carré-Duchamp. Okay, for some suitably defined Ct, such that as t tends to infinity, Ct should go to C. Okay, this is what we mean by a local Poincare inequality. And this lemma is a technical lemma, but it's going to be very, very instrumental in our proofs. We will show that this local Poincare inequality indeed has an integral form. Okay, it can be written as the integral of time of the Kare-Duchamp of some push forward. This is just technical, but we need to work through this, of push forward of this operator ds. So the integral is with respect to s. Okay, this, even though it looks like it's just some integral calculation, is actually quite important, because this is going to let us show the following statement. Okay, we'll use this to show the following, that if indeed the Kare-Duchamp, so if you have the Kare-Duchamp of the push forward is less than alpha s of the push of the non-push function. So look at this. F, this is a push forward of us. So essentially, I want to see how last time we saw how a function push forward behaves. Here we are looking at how the gamma function of the push forward behaves effectively. Okay, we are saying that suppose you can show such an inequality, that means you basically have a non-asymptotic Poincare inequality. Okay, so you can see that this is going to be an important thing when we go all the way through. Okay, all right. So first let me prove this particular statement. This is problem 212 in Ramon van Handel's book. It is the following, that this difference is equal to this. I'm going to spend a few minutes on this because I sweated it out last night in one of the steps of this proof, which I thought was wrong till I actually figured out it is correct. So just I want to, it's catharsis, sharing the pain, whatever you call it. It's that. Okay, so the first step is the following, which is the following. Let's look at this. Let's look at the derivative with respect to s of p of t minus s of this function square. So there should be a parenthesis here. Let's write this parenthesis. Okay. So this is the function. So I'm going to tell you something which is wrong, but it took me a long time to figure out why it's wrong. Okay, I'll start with that. I think it's worthwhile because these are the kinds of calculations that every step it's inside. So the calculation is the following. Okay, I'm taking a derivative. So it's a function. It's of the form g of h of something square, right? Internally, it's something of this nature. That's how this function is looking like. So if I do chain rule, it's derivative of this times derivative of that times derivative of this. I just chain all that's true. If I do that, the derivative of pt minus s is minus L pt minus s. Okay, then I need to do chain rule. I need to multiply this by the derivative of this, which means I need to multiply this according to this reason to 2 times ps of f times the derivative of this, which is L ps of f. So I should get this as the expression if I do the chain rule. Does it make sense what I'm saying? Instead, I'm writing a plus here. And this is critical for everything you need. So what am I saying which is wrong? And it turns out what I said cannot be algebraically manipulated to this. So I'll spend 30 seconds for you to look at this and just go through calculus and realize what I said is fundamentally broken somewhere. So chain rule says f of g of x, if I want to take the derivative, it's f prime of g of x times g prime of x. That will give you some very, very different expression. It is not going to give you this. No, I thought that. So he said it's an operator, so something may change. No, chain rule still works through that way. Why are you getting a sum?
It depends on S.
But that chain rule should take care of all such dependencies. Okay, I'm not going to, it took me a long time, embarrassingly long time to realize this. But the big problem is this is not a derivative with respect to x. It's a derivative with respect to this subscript s. It's a time derivative. So why does it, so chain rule this is not a chain rule. You should think of it as a product of these things, even though it's two operators. That sounds very flaky, right? Thinking of it as a product of two things, even though this is a function of this, you shouldn't think of it that way. And to convince myself, I actually did it from first principles. Okay, so why is this even true is the following. Okay, so let's actually just go back and lose the definition of a limit and try to figure out what is happening. Okay, so derivative with respect to s means I do s to s plus h, s to s plus h minus s divided by h. And then maybe this is what, and then you add and subtract. Here you fix an s, but here you look at s plus h. Okay, I'm going to separate the inner and the outer. Then because of the summation, I get two separate terms. Now look at just this inner term. Okay, in this case, as h tends to 0, s plus h tends to s. So this part is just going to remain as ps of f. The ratio with respect to h appears on this side. And so this gives you minus L pt minus s of this. Now look at the other part. In this part, t minus s is fixed, s plus h and s. I need limit as h tends to 0 of pt minus s of this difference. But I can now, because pt minus s is linear, I can pull various terms together. Okay, and then I can swap this limit and this. Now I'll get 2p. Now I can use chain rule, the actual chain rule, to do this. So I'll get the sum of these terms. Okay, so this behaves as though I take a derivative of this. I treat this as a product of two functions. I'll take a derivative of this, apply this function to it, plus derivative of this with this. Yes, that's correct. But I wasn't. That sounds a little flaky to me. Maybe that is actually correct. So I went back to this and did this. So it's not a. So be very in this. So why I spent so much time on this is at some points we're going to take derivative with respect to x, and some points we're going to take derivative with respect to s, and the equations are going to be very different. And if you're not careful, I had some other mistake in my notes which I fixed early this morning. That's why I pushed a new version through. So be careful when you're doing all these calculations. That's the point of all this discussion.
Subtracting h in the outside and adding h in the inside.
I can do what I want. I've just added and subtracted.
Here, why are we subtracting h inside?
Both. I'm doing everywhere. S. What is derivative with respect to s? S should be replaced by s plus h everywhere.
Yeah, it's minus h.
This parenthesis, it's minus s plus.
What?
You're saying it's
Now it means
t minus quantity s plus h.
okay, yeah.
Oh, I see. Okay, yeah. Thanks. Yeah. This is t s plus h, which make a minus. Okay, that's all. So that's all. So yes, as Sundar pointed out, it's just in operators is a product, but it is not very apparent, at least to me, when I write it out this way, what exactly is going on. So be careful. In various calculations that we are doing, we are going to do all sorts of derivatives, and you can get messed up. Okay. Let's go back here. Okay, so I will follow some things line by line, and other things I'll say you check yourself. So let's just finish this one line by line. So the derivative of this is minus L pt minus s ps of f the square. Then pt minus s applied to this one, 2 ps of f, L ps of f. Now I can swap L and p, so L can go inside. I can then pull this p common out. I still have a negative sign, so this positive sign becomes negative. So I'll get this inside. So I'll get L ps of f whole square minus 2 ps of f, L ps of f, which is nothing but so this is the definition of the gamma function for this as g. If this was g, this is L of g square.
This gamma pairs, this P and L, you have this.
Let's pull the expression. Sorry, yeah. Okay, it's just now the definition. Sorry, is there a mistake?
No, it's the right side. You're using that P and L commute, right?
Yes, I'm using P and L commute all the time. Okay, that we saw that in Kolmogorov. This was from Kolmogorov's equation long back. Yeah. Using the fact that P and L commute, we have gotten this. You are talking about here? Okay, so
When it's -2 times.
yeah, exactly. That exactly. For that -2, I use the fact that P and L commute. Now, so what I have is a derivative of this is this. This is very useful because now we will do fundamental theorem of calculus. That means the integral of this over appropriate limits 0 to t must be this quantity at t and this quantity f s. Okay. Now let's look at this quantity inside. As s becomes 0, ps of f is identity. Okay, when s is 0, ps of f identity, and this is just pt. So it's pt of f squared. When s goes to t, this becomes identity. This is just pt. We get pt of f whole square. So this relation is going to be useful. A lot of times we are going to use this, but because on two extremes we get actually these operators collapse. One will be an inside and one will be the outside, and that's very useful property we are going to leverage again and again. Okay. So this essentially gives me so we have basically proved this, okay, that this difference is this. So what can we do with this? Well, first we have the following. Suppose that you have this is the push forward of the gamma function. This is the gamma function of the push forwards of the function. We want to see what the relation is. Suppose that this intuitively, okay, this is getting smoother and smoother. Okay, the gamma function, at least for the kinds of things we are looking at, your mental model should be it's nothing but the gradient of the function square. Okay, remember what is the carré Duchamp for the Gaussian? Okay, let's go back. It's a gradient of f squared. So if this function is becoming smoother, this is becoming smaller. Okay. We go back there. So this is getting smaller, but this is also getting smaller in a different way because I'm pushing this forward of some other function. So both are two things decreasing. PT, it's push forward of some. No, actually, right side. Wait, something is what it is. Wait, something is wrong because no, yeah, it is. This is a function, and I'm pushing it forward. It's smooth. No, PT is anytime you do a PT, it's a smoother. PT of G is a smoothing function. Okay, for any G. So there are two ways, there are two different ways. One is the function is getting smooth, the other is happening because the gradients are getting smooth. Rough. It's a smooth, it's first plus a second order kind of thing. Okay, roughly. Okay, that's not quite correct, but these both, at least you agree, both are getting smooth for different reasons. Okay. Suppose that this relation is alpha of s. Okay, then this implies that sort of local variance satisfies a Poincare inequality. That's the statement we are going to prove. Okay, so let's prove this. So we go back to this expression we derived, which is pt of f square minus pt of f the whole square can be written in this integral form. This is what we spent this doing this calculation right now. Okay, so now we know that the smooth gamma function is bounded by assumption alpha s times the smoothing of the original gamma function. So let's just stick that in here. Okay, so this is being we can essentially pull this ps out. But then pt of minus s and ps, because the semigroup, they collapse together, just giving you pt. This collapses to just give pt. So this overall thing is pt of gamma ff, which does not depend on s. So this whole thing pops outside the integration. If it pops outside the integral, then all I'm left is the integral of alpha of SDS. Okay. So that's what this result is saying, that this integral of alpha of S is CT, and then you get this. So this kind of an inequality implies this. Okay. These are just lemmas we are going to use for building up our thing, but yes. So
Here, gamma of F is not going to zero. It's just
I'm not saying anything about going to zero. I'm just saying there PS. My mental model is PS is a smoothing operator. Where it's going is not clear to me. But
I think alpha of S should be, or that's just wait.
we'll wait and see. We'll wait and see what it is. Okay. I'm just showing you. Suppose you had such a thing. This is what you would get. So this is the main theorem. This relates the Bakry-Emery criterion, which is a purely algebraic criterion, to the Poincare inequality, which actually involves an integral on both sides. Okay. The Bakry-Emery criterion says, look at the gamma function and look at the iterated gamma function. So what's the iterated gamma function? It's one more step of exactly what we did. We defined the gamma function by the L operator. You can think of the iterated gamma function as the correction, the linear correction, quadratic correction for the gamma function itself. Okay. So L gamma Fg minus gamma FLG minus gamma LFG divided by 2. It's exactly the same definition at one more level. Next. What the Bakry-Emery criterion says is that if C times gamma 2 is bounded by gamma, or equivalently if gamma 2 by gamma is strictly bounded away from 0 by some constant. Okay, that's what 1 by C. Okay, if you have this ratio strictly away from 0, if you can satisfy this condition, this implies the way we are going to use it, this implies a local Poincare inequality, which now you can use as t tends to infinity. This local Poincare inequality this is just a variance as t tends to infinity. That's how we started. As t tends to infinity, pt of gamma we saw is just the Dirichlet form because it's just p infinity, which is just the averager. So it implies the Poincare inequality as a special case, and therefore from our previous class it implies at least variance goes down exponentially fast. Okay, this is stronger. This is a strongest. This Bakry-Emery criterion implies something stronger. It implies a local Poincare inequality, a corollary of which is a Poincare inequality. Okay. So, correct. In the middle, we will use a third statement which is useful, which is sort of how does the smooth gamma function decay. So the relation between the smooth gamma function and the smoothing of the original gamma function. Okay, yeah.
sorry, just so what is the Criterion show for like Longevity dynamics?
We are going to do all that. So after I finish this, I'm going to actually calculate everything through explicitly, which is what I was sort of complaining about at the beginning of this thing. But to answer your question, this is the iterated Criterion for the Langevin dynamic. Okay. So it's e to the minus w. Okay, is the pi star is e to the minus w divided by up to normalization. This is the iterator. I'll get to this, but since you asked me, I showed this, but we will come and derive this. So it's an explicit form. So that is the point, that you can actually derive these things explicitly when you can when in general with just an integral you can't do anything. Yeah.
Okay, although you mentioned that this Bakry-Emery criterion is related to differential geometry, right?
Yeah, see this C is called the Ricci curvature. Okay, the ratio of gamma 2 by gamma is the Ricci curvature. Okay, so there's many of these things.
Failure of that is going to, or any difference in that is going to somehow relate to the curvature.
And the manifold is based on functions.
So I'm stripped out all the differential geometry out of this. If you these results hold in much greater generality than what I've stated. There's a book by Bakry and Emery and others, I think, in 2014, Markov processes and differential geometry or some such title. I don't remember the name of the book, but you can see much more about this one thing. Okay, thank you. Yeah. So there's a book mid 2010s. I think it's 2014. It's a yellow book. So I borrowed bits from there and there, but simplified greatly to this setting because I'm just interested here just in RD, finite dimension, nothing fancy. So, but you can go down this road much more broadly. Okay, so we need to prove these three statements. Let's prove that 1, 2, and 3 are equivalent to each other. So let's start from 2 implies 3. So what we have is local ergodicity, meaning this is true. The gamma of the smooth function versus the smoothing of the original gamma function. Suppose that this is exponentially smaller than this. Okay, let's assume that's true. Then, what is the difference in variance? Well, from our lemma, which we just proved right now, let's go back to our lemma 2b. Lemma 2b proved that if we have such a relation, then we immediately have this, where this constant is nothing but the integral of that. So this is just a straight application of what we did. Okay. So this also answered what those explicit constants are. Jacob's question on what this constant what alpha would be. So where am I? Sorry. Yeah. So this is my alpha. And so all I need to do is integrate that and stick it in. And what I get is this. It is just integral of an exponential. And that's all there is to it over some finite interval. Good. So 2 implies 3 is immediate, essentially, from whatever things we built up. Next, we will do 1 implies 2. Okay, that the Bakry-Emery criterion implies local ergodicity. So we need the derivative. So let's start with the derivative of Pt minus S of gamma Ps of F, Ps of F. This is what we spent some time thinking about before. Start with the same thing. So you can write this as if you take the derivative with respect to S. So this is where I'm going to sort of skip through. I don't expect to read through it. There's a lot of algebra steps in this chain. What you can show eventually, so this is what I want to skip through, is to say that this derivative can be written in terms of gamma 2. Okay. The reason gamma 2 appears is by manipulation, you'll get L of gamma kind of terms. And if you play with it, you're going to get gamma 2 out of it. Okay. To actually do this very carefully will take me time. And it's the same kind of calculations we did before. There is nothing new. You need to think of it as operators, and therefore you shouldn't think of it as a chain rule. You should be careful in these calculations. And then this will turn out to be true. Okay. But it is just sort of very careful differential calculus. Nothing more than that is going on to get this. Okay. So what this leads to is the derivative of this can be written as in terms of gamma 2. And now the Bakry-Emery criterion says gamma 2 is at least 1 over c times gamma itself. So now we can substitute this and get the following. The derivative of Pt minus S of gamma Ps of F, Ps of F is this gamma 2. I can use this inequality to get back to gamma. Again, this thing I've circled in red is an interesting object we have seen for the following reason. In the limit where S tends to T, it becomes the gamma of PT of F, PT of F. In the limit where S tends to 0, it becomes PT of gamma of FF. Okay, so this allows me to interpolate between these two ends. So we will look at this object again and again. Okay. And now what we have is that this object itself satisfies this differential inequality. This is non-negative, and therefore I can take things, I can divide on both sides without being worried about sign flips and so on. Okay, so I can divide both sides by, so I can get d by ds of this divided by this is minus 2 by c. Okay, and therefore this is nothing but the derivative of log of this function is negative 2 over c. And so now I can integrate this between the two limits and use exactly the same fact I use. At one end it's 0, at one end it's pt, and one end is p0, which is identity. And so what we get is log of p0 of gamma of the push forward minus log of pt of gamma of the original function less than e to the minus 2 by c, which means the gamma function is exponentially decaying. Okay, so local ergodicity implies, Bakry-Emery criterion implies this local ergodicity behavior. And then the third part, now we'll close the cycle. 3 implies 1. If you have a local point array, that implies a Bakry-Emery criterion. So again, we go back to the same form that the sort of local variance can be written in this integral form. And therefore, this minus this is 0 is greater than or equal to. I can take this to the other side. I can take this to the other side and use this bound. What did I do? Second. I'm using 3. I'm going to copy that and paste it. So we have this. This is our assumption. I should have copied it earlier. Sorry. Copy. Put it in so that we see where we have that. Otherwise, we can't track stuff. Okay, this is what we have. This is by assumption. Okay. So we can use this from 3. We have the following. I'm just pulling this to the other side and getting this minus that greater than or equal to 0. Nothing else is going on. And therefore, now this difference, now we can use this lemma. We know that the difference between this is equal to this. So we stick that in. Okay. I'm going to be careful only in the first part of this calculation to show you another trick that is used like several times in these proofs. Fundamental theorem of calculus says that h of s minus h of 0 is the derivative of h of u du from 0 to s. So let's do that here. So this whole thing is a function of s. Let's think of this whole thing of some h of s. Then I can write this as h of 0. So when s equal to 0, there's just pt. P0 of f is just f. So h0 plus the integral, let's put this dummy variable u in, the derivative of this, when this is the variable with respect to u, d by du of s has become u, du, over the range 0 to s ds. Okay. It's okay. I'm just being very careful. I'm just writing standard calculus, nothing fancy. The other part is just left as is. Now, we saw the relation between, this is what I skipped. I just showed you sort of few of the steps. Derivative of this is related to the gamma 2 function. Okay. Now I have the derivative of that inside there. So I will stick in the gamma 2 function there. Okay. So all we have done is this derivative is replaced by the gamma 2 function. This -2 interacts with the 2 and the negative to get -4 and all that. If you trust my algebra, then I'm just going to point out sort of what are the key things that are going on here. Okay. That's what is happening here, that because of this. So once I have this, I can do one more time. So I can, so you do that. The goal always is to pop things out. So let's look at this part of it. So we did the fundamental theorem of calculus to sort of write it as something plus some integral of something else. Look at this something. This is not an integral with respect to t. It's an integral with respect to s. And this, because it's an H0. So this thing just comes out of the integral. And this integral of ds from 0 to t is just t. So what you're going to get, each time you pop things out and try to get constants out, remaining term will fall into some other integral, the same kind of trick. And eventually what you're going to get is function, you'll get a little o of t square term along with, because double integral of some constant will give you a t square term, okay, if it's a constant term. Okay, so that's where I want to just show you where these kinds of objects are popping out from and what kind of manipulations are leading to that. That's really my takeaway. So each time you pull out a constant which does not depend on the integral term plus something else, which will become a higher integral, and try to bound the last thing in some manner. But in between, you'll get order t terms, you'll get order t square terms, and little o of t square terms. Okay. So this is what you're going to get. If you just go through the mechanics of what we have done, which is just this one trick, yes. But you're doing it in a certain way, very carefully. You're doing step by step. Each time you're just pushing everything else to one more term. They're all, it's calculus in that sense, yes. Okay, that's all you're doing here. So what you're going to get is order t square term. You can pull it together and you will get a gamma. You'll get an order, There's a mistake. I think I wrote this is wrong. This is correct. This I think is wrong. I'll fix it afterwards. Please ignore this thing. Something is wrong here because this is meaningless. I've written something wrong here. I'll fix it. When we started from 0 is greater than or equal to a bunch of equalities, this. That means it shouldn't be this, it should be this. I think this is correct, but I'll check it I'll check it after class to make sure and update it if this is correct. So the point is, this statement is true for any t greater than or equal to 0. So I can take limit, I divide both sides by t square and take limit t going to 0 to get t criterion. Okay. So that's the proof. So you see, it's essentially there is nothing magical going on in this. You just need to be very, very careful with the calculus in the timed variable. That's basically what's happening in this proof. Okay. And so what we have at this point is the Bakry. So let's go back here just in case. Now that we'll treat this as a black box. And to be honest, we will never use these kinds of machinery again in this class through the semester. We will use this as a black box, but not this kinds of sort of very careful calculus type calculations. you're not going to see it very often. So this so what you'll see later is more probabilistic calculations, which are somewhat different in flavor from this kind of basically differential calculus type calculations. So this is what we want, 3. We are going to now show we can explicitly do 1. Okay, and again, this will address sort of what Constantine brought up at the end of last class. Okay, here is the statement. Let mu be a density function, which is proportionally e to the minus w. X is an RD, where w is a rho strongly convex function. Meaning, look at vi, vj are dummy variables. Del square w by del x for all v, the second partial of w, vi, vj, the summation over all ij must be greater than or equal to rho summation vi square. This is the strong convex. This is a rho strongly convex condition. Okay, that's all we've said. Okay. Or equivalently, mu is strongly log concave. Okay, with parameter rho. Suppose this is true. So it's such a distribution, but okay. Then look at the Langevin dynamic sampler associated with mu. So what do you do then in this case to build? If this was the distribution you want to sample from, you would basically use your drift from as grad of w. When I do log of this minus w, yeah. If I do gradient of this, I'll get minus. I will get. When I do log gradient, I will get this. Yeah, okay. So this is what I'll get. I'll get grad w as the drift xt plus root 2. This is standard Langevin dynamics. So what do we remember for this process? We did it when for the Langevin dynamic, we got the following. The generator was the inner product of w comma f. That's what we said. The regular inner product, which is explicitly del w by del xi times del f by del xi, the sum over all coordinates. It's a minus of that, plus the Laplacian of f, which is nothing but del square f by del xi square. Because, yes. I derived this for the, did I derive it for the, let me see, give me good question. I thought I did it at the end of Markov process. Okay, this is all OU process. Or point curve, let's see what, did I just state it? I didn't even do the scalar case. This is all Gaussian. This is Gaussian. This is not Langevin. So at the end of this, we did L star. We explicitly derived L star in very long back. Remember, from first principle, we did the L star because we derived the Fokker-Planck equation, which is the L star for this operator. But I thought we did L. Anyway, I will check. If it is not, I will try to write something up and put it there. Okay, out there. So for the Langevin, this is the thing is grad w comma grad f plus Hessian of f. That is L of f, which is what is explicitly written out here. And the stationary distribution is e to the minus w. Okay, yes, normalized appropriately. The claim of this theorem is that for such a process, if W satisfies this strong convexity property, then the variance of F is bounded by 1 by rho times the Dirichlet form. Okay. That's the claim. And we want to prove this. So the way we are going to prove it is just check that the Bakry-Emery criterion holds. and therefore a local Poincare inequality holds, and therefore the asymptotic Poincare inequality holds, and therefore you get exponential. This is the asymptotic Poincare, and therefore you get fast mixing. So that is the rule. So to do that, we need to explicitly compute gamma, L of gamma, L of F, L gamma. All these objects need to be explicitly computed. I'll compute a few of these things to show you how these calculations look like, but not sort of do every one of them, just so that you get a flavor of how these calculations go. Okay. So we need to compute the gamma function. So the definition of gamma is L of F square minus 2F LF by 2. That's the definition. So 2 times gamma is L of F square minus 2F L of F. Good so far? I'm just pulling the definition. So what is L of F square? Okay, L of F square. So I just take L of F and replace F by F square. If I replace F by F square, this one becomes 2F del F by del X, because F square chain rule. This now it's all derivatives with respect to X, not with time. Okay, now we have switched to derivatives with respect to the Xi's. So derivative of this is 2F del F by del X. This one, when I put F square, the first derivative is that, then I need to do the second derivative on that and get an expansion. If you do that, I'll get 2F del F by del X for the first one. I will get, for the second term, the F square, I'll get F del square of F plus del square of F the whole square. You can check by yourself. I'm just showing you that's what that calculation will lead to. Similarly, I have FLF, that's F, and then the LF is written out. Expand this out. So there is a F del W and del F. There's an F del W and del F. This cancels. There's an F del square F. There's an F del square F. This cancels. So what you get is therefore 2 times del square F square and nothing else left. So that's how you get. So you were asking at some point last time, how did we get that the Carré-Duchamp is just grade F square? Here is the proof. Okay. Just explicitly just write these things. But you see, it's not, you don't do any this is really why this method is powerful. That you can just use these differential forms and just grind through it and you get these things. There is no integral with respect to some unknown distribution or known distribution, but you don't know what to do with it. Yeah.
We knew that Dirichlet form is expectation of this mu, right?
We never, yes, for the Langevin, we didn't, we proved the following. The Dirichlet form is nothing but the integral, is the expectation with respect to mu measure of the Carré-Duchamp. Yeah. But here we have just, for any Langevin, we have explicitly told you what this is.
Yeah.
Okay. So you could ask, so do I know the Dirichlet form? Not really, not explicitly. You know it as the integral of this, but I don't know how to do that integral in an explicit form in this sense. Okay. Next, we need L of the gamma function. So this is nothing but this function. So again, stick this in. This is nothing but the summation, the norm square is nothing but the summation del F by del X I square, sum over all components, grind through the algebra. Again, you're going to get a certain expression. Okay. I'm not going to show you all the steps, but I'm just showing you what is being done. Okay. We need the Dirichlet form of FLF. Exactly the same thing. You work through the algebra of this, and what you're going to get is L of F square plus F L square of F plus 2 times the inner product grad F grad LF. Okay. None of this is magical. It is just cranking through definitions. Okay, and sort of quote unquote elementary differential calculus. And you build upon this stuff. So now I want gamma of FLF. By definition, that is half of the generator of FLF minus L of F square minus FL square of F. Okay. Now, L of FLF, you have this, stick that in, various terms cancel, which gives you a nice clean expression of this grad F, grad LF. That's what you get here. Which you can write again in explicit form. Finally, now I'm on the Carré-Duchamp, or the iterated Carré-Duchamp. It's L of gamma F minus 2 times gamma FLF. Well, that's what we build all this machinery, all these calculations for. We have this, we have this. You stick it in and just simplify to get the following. That gamma 2 has this very clean form. Okay, we can actually write. So note that so far there's no inequality. Everything that has been written so far is all equalities. Okay, just calculations. Okay. So which means that gamma 2 is something non-negative plus this, which imply, because this is nothing but grad F inner product with respect to itself, which means that gamma 2, this is the first inequality we see in this whole train, is gamma 2 is greater than or equal to the inner product of F with gradient with Laplacian of W times gradient of F. Now use strong convexity of W to bound this by rho. Okay, this is the way your strong convexity is used. Okay, and therefore you have and this is gamma FF. Yes.
Is it Laplacian of W?
Did I?
Your delta of W.
Let us see.
Sorry.
Let us see what I have.
No. Oh, it's the same as the index quantum above. I'm sorry. Yeah.
It is correct.
Yeah, sorry. That's right.
Okay, so even though I didn't do every step of this, you get a sense of how these kinds of proofs work. It is okay. That's really what I want to convey through this business. And so this whole arc has gotten us to showing that for Langevin dynamics, you get exponentially fast mixing independent of dimension. Okay, if the function is strongly convex. Of course, in practice, most things we care about is not strongly convex. Okay, so we'll talk about that starting 2 lectures from now on beyond this. So, but I wanted to bring the theory up for this Markov-Prossi, just as we'll use these things for other proofs and bounds later on. So this is a good sort of starting point. People will say, oh, let's assume an LSI. When you start reading papers in this space, you'll assume LSI or Poincare or something. Now you know what those things mean. Okay, that's really the point of all this thing we talked about so far. Also, this is the starting point of a major line of research among certain parts of theoretical computer scientists, probability theorists, and so on, which of something called the KLS, or the Kannan-Lovász-Simonovich conjecture, which is essentially the following. What we have seen is that if the function is rho strongly convex, if the distribution is rho strongly concave, then the Langevin dynamic converges exponentially fast. What happens if rho equal to 0? Okay, the conjecture is that even if mu is log concave, not strongly log concave, then there exists a C. Now you can't use a strong convexity parameter. There exists some constant such that the Poincare inequality holds with parameter C. Okay, this is the KLS conjecture. Why do people care about it? This is sort of far away from what I do, so I can just give you some summary. It's not going to be very deep, what I'm going to tell you. You want to look at this paper by Intatli and Santosh Vempala, which talks about why this is an important statement. This is taken from, which I found this sort of image very, very nice. So the KLS conjecture is here. There are lots of implications on very fundamental problems across geometry, probability theory, and computer science, if indeed the statement, what I said, which is even for rho equal to 0, the Poincare inequality holds. If that statement holds, then a whole bunch of other important things to do with concentration of measures, sampling in very high dimensions, certain optimization problems in high dimensions. There's a bunch of connections. If one is shown, then a whole bunch of other things are true. So this particular thing we talked about lies in the center of this whole business. So people have been spending a lot of effort building new machinery to address this problem of rho equal to 0.
All know.
These arrows are things which you know. If this is true, this is true. If this is true, this is true. Each one is a paper. These arrows are paper. These are papers in the paper.
ALS is, because I mean, central limit theorem or like reverse.
A certain high, it's yeah. What exactly the reverse Brun-Minkowski inequality here means? I don't know what version of it. Okay, it's something to do with in high dimension. How does dimension dependence look like? That's essentially the question. All this is about dimension dependence issues. Yes, I don't know too much more about. I haven't read almost any of these papers, just to be clear.
The problem could have,
It,
or is it a?
it's a so if this conjecture is resolved, then some conjecture on high dimensions, on the hardness of high dimensional sampling, or some conjecture on the optimization is true. Each box is something about dimension dependence hardness of a particular problem in that box. Yes. Good.
Say that to me seems to be, even if the
Here it is.
equilibrium measure, yeah, it's
Even if rho equal to 0, okay, meaning
not
it's not strictly strong convex, it's just convex. Suppose W, in this language of where I've said this, if W is a convex function, not a strongly convex function. Okay?
in 2 dimensions, x1 squared is a convex function, for example, and the equilibrium measure for that has no Poincare inequality.
There's no
I see that,
equilibrium.
That's right. It has no
Yes. So that's what. So what this is saying is, I already have a semi-group and all that stuff.
Give me a
I give you a Markov process. Correct. Sorry. I give you a Markov process. So this whole setting this goes back to a question Gustavo asked 2 classes back as well. I'm always dealing with Markov processes which have a stationary measure of mu. That is the setting. Okay. In fact, this is also a reversible Markov process with a stationary measure of mu, with a generator of L, and that stationary measure, sorry, I should have been more careful in saying this, is of the form e to the minus w, is proportional to e to the minus w, where w is convex. That is the statement. Okay. Let me finish one. Do you want, what do you want? I wanted to say one more thing here. Yeah, the other thing I wanted to say is the following. For this class of problem, now that we have stated exactly this problem, what is known today? As far as I understand, the constant the people have gotten to is root log d, 1 by root log. I guess C should be 1 by root log d. That is where people have gotten. So there is a dimensional dependence. You want a universal constant C. They haven't gotten the universal constant C, but if you don't make any assumptions, then you can have poly D or whatever. You can have bad dimensional dependence in these problems. Okay, what the state of the art as of I think very recently is root log D in the dimension dependence. Now coming back to your question.
The computation of gamma. Yeah, gamma. So I don't see why you should actually ignore that first term. There is equality between grad F and grad F.
No, I'm just saying it's non-negative.
But if you keep it,
Uh-huh.
then if you go to the next step, you can apply strong convexity for second term. You can actually improve that down to 2 times 1 plus rho times. But in that case, when even and rho is equal to 0, we get a non-trivial lower boundary.
I don't want to think online because this is not so. Let us see. You pull this in, so you're saying something I've written here is wrong. That's
Yeah, rho equals to 1 in this inequality.
so something is wrong. So I think I've maybe there's a mistake in my calculation somewhere. We should go back and check because it's not true that if W equal to 0, this is true.
Yes, I think the step between the index formula line and the second line, you have the coefficients of the Hessian of f squared. You've accidentally swapped them perhaps for the gradient of f squared.
Maybe, yeah, I think.
Whereas the coefficient of the Hessian of f squared is non-negative, and this inequality is useful then. If we swap it, like there's in practice the index notation, the gradient notation, we made a mistake.
Okay.
But the resulting inequality is correct.
Okay. Thank you. That's very useful. Yeah, as I said, there are bugs as I was writing. I discovered several this morning and fixed it. There are still a few left. I'll fix it after class today. Okay. So yeah, this brings me to the end of this arc of the Poincaré story. So let me, for the next 5 minutes, give you a heads up of what we will see next class in terms of the theory in this line. Okay, so the we use Poincaré to show that the variance essentially exponentially decays. The push forward variance exponentially decays. Can we show something stronger? So it's exactly the same setting as before. PD is a Markov process semigroup. A Markov process, L is its semigroup generator, mu is its stationary measure. Let's define, I'll talk about this in greater detail next class. Let's define the entropy of entropy of a function f as the expected value of f log f minus expected value of f times the log of expected value of f. Okay, we will see that if f is the Radon-Nikodym derivative, or is equivalently is the likelihood ratio of two distributions, then this definition of entropy is exactly the KL divergence between nu and mu. Okay, but something important to note: this is the backward KL, not the forward KL. We'll worry about forward and backward KL when we talk about autoencoders, very short autoencoders very soon. But what do I mean by the backward KL? It is the averaging is taken with respect to mu, not with respect to nu. Okay, you could define things different depending on what you want to. We'll worry about what the implication of these things are. KLPQ versus KLQP, they have very qualitatively very different things when you're trying to build systems, and we'll come to that and connect it to something called mode collapse. This will be like 2 lectures from now, but that's what this entropy is. It's just KL nu mu, which is nothing but the log of the density ratio with respect to the first, because KL is always the integral with respect to the first coordinate. That's the KL. Okay. So this F entropy with respect to mu is a KL nu mu. That's what you get here. And the theorem, which we are going to talk about next time, is the following. So we saw variance decay. Instead, we can talk about entropic exponential decay. So does the entropy itself, the F entropy and the push forward F entropy decay? It's a stronger statement than the variance decay. Okay. Essentially, this is a KL divergence. So this happens if and only if a modified, so means of the Poincaré inequality, something else is required. The inequality is called the modified log-Sobolev inequality. I'll talk about why it's called a modified. I'll use the word log-Sobolev inequality because just saying modified every time is just a mouthful. I'll call this an LSI, so though it is a modified LSI. It says that previously we had variance less than or equal to the Dirichlet form. Here it is entropy less than or equal to the Dirichlet form of not f and f, but log f and f. It's different functions. We'll see what these things mean next time. Okay. So if this will imply this, and further under some this quantity indeed, so this sort of this the push forward of this modified Dirichlet form will also decay exponentially. So we are going to prove this. Do the calculation of this for Gaussian and then show that essentially analogous to exactly the Bakry-Emery criterion, we can do something very similar, that the Bakry-Emery criterion implies something like what we wanted. Okay, that is the next arc. So it's a strong. So we are getting sort of, instead of the variance decay, we are getting entropic decay. So that's what, when people say we'll assume LSI condition holds, in many of the papers, theory papers today in sort of diffusion world and all this stuff, they'll say if LSI holds, something happens, and there's a lot of machinery. This is basically the lecture needed to sort of just pass that literature. I have a closing comment in this, that for those of you who have taken a class in concentration measure, you have seen sort of the Efronstein inequality and then the log Sobolev type thing leading to Telegrams type inequality. One was giving exponential concentrations, the other was giving sub-Gaussian concentrations, e to the minus x squared minus versus e to the minus x. It turns out this is exactly the analog of that. Going from variance to entropic decay is the same kind of machinery which allows you to go between sub-exponential, sub-Gaussian. Basically, you tensorize variance. If you're familiar with the concentration of measure literature, if you tensorize variance, you'll get the Efronstein. You tensorize entropy, you got log Sobolev inequalities and Telegram type things. This is exactly the same kind of thing. You're not looking at FF, you're going at log F, and you have a log. So roughly, in the Gaussian case, this is, I think this is, let me see, I want to leave it with this. Okay. The Poincare inequality was of this form. The variance E of F square minus E of F the whole square was less than or equal to C grad F square. What we'll see here is E of F square log F. So it's stronger. It's a stronger inequality. Okay. And this gives you entropic decay, that gives you variance decay. Okay, that's what we will. So this is just a heads up of what we'll do next Tuesday.